or better solutions.
A dumb question to start off with. Why was the MLM a new task? It seems like something that would have been fundamental. Like the masking thing, it seems like a fill in the blanks kind of thing to me. Why wasn't it already a task in the core NLP? Like, do you have some context to provide on that?
Danny, can you repeat the questions?
So, but.
Or someone repeat
on.
questions for the camera, or like summary?
So do you want to? So the question is, why didn't core NLP pay attention to the mass prediction task? And the answer is they did. It's not that brand new of an idea. It's brand new here because they're combining it with the transformer network architecture. But I have a precursor to that question, which is when you mask, do you predict, so the masked words, do you actually go predict, do you have a softmax layer where you predict a token, or you predict the representation for the masked word, or both?
To represent.
I'm pretty sure, so in the output, in the final layer, you have a vector for each positional token, and I believe they're applying a softmax on top of each of those.
Right. So the signal comes from the softmax.
Yeah.
If you predict it wrong, the representation isn't good enough.
Right. And that's where the loss is coming from.
Yeah, I think they do something slightly tricky to that. They add some noise to the actual mask target itself. So I read something like 10% noise on top of the 15%. But like 1.5% is kind of random.
That's right.
So
that's the additional complications they add to the mask task, which has been around since the 1950s. It was just called the closed task. Close.
Yes.
So what is, I guess, related to these questions for that particular task or pre-training, whatever you called it, what is a loss function? Is it a softmax and then are you predicting the right token?
If it's a softmax, it has to be cross entropy.
Yes. And you're predicting, I guess, across the vocabulary.
Yeah.
You're classifying the mask token across all the possible words in the vocabulary.
Yeah.
Which is
Insane.
the same as word2vec. They use this other system called noise contrastive estimation, which instead of just a softmax, contrasts it with a few negative samples, because you don't have negative samples usually. You need to have signal for both, is the correct word.
And then there were like 3-4 steps in training. Like there was the blank filling thing, and then there was sentence prediction.
And those are the only two tasks.
Okay, so you only use these two tasks to train the network.
That's right.
And you just change the loss function and like retrain all parameters, or are you just fine tuning?
For the
second
for
task.
another NLP task?
No. So you have two tasks to train the network, right? So you train it once on filling the blanks, and then what do you do? So you change the loss function and just fine tune parameters, or
Same parameters, yes.
Okay.
Just continue to update them.
Yes.
oh, continue
With the next task.
Right.
Yeah.
Okay.
That seems like a sensible approach. Do we want to answer questions or go to discussion points?
Let's take questions.
If there are clarification, I guess.
Yes.
Okay. So far, it seems like all the benchmarking performance are not text generation. Is that right?
Yes, most of these are natural language understanding tasks.
So I'm under the impression that OpenAI GPT can do text generation. So, sorry, this is kind of an open-ended question. So, what would you think could possibly enable it for text generation task?
Oh, for this?
Yeah.
Well, I was thinking that maybe you could combine this with a stacked pre-trained transformer encoder. So I thought about this, that this doesn't even make sense.
So,
could you set something up so that you had a couple of words that would start off the prediction, and then everything was masked from one point on, and then it like predicts something?
Try to predict all the maths.
And it should have some distribution, right? You might have to do something like when you loop whatever it's called when you loop it, you just make it keep until it converges. Is it Gibbs sampling? When you put some noise in, it spits out something that's roughly a sentence. You pipe it back in, and it moves it towards an actual sentence. I think it's Gibbs sampling. Gibbs sampling. Yeah.
Did that answer your original question?
Well, it probably takes much more than that.
We're incapable of answering it. So I get the question. So in recurrent networks, or in the original neural language model by Bengio, it was trained to predict the next coming word. Right. Therefore, it can generate a language. We can basically give it a few words. It's capable of generating the next word, right? We can call it natural language generation. This, because the mask can happen anywhere, it's not necessarily that. But I think then it has a lot of, I think the point in here is that you have a lot of this structural information that you wouldn't have otherwise because of the self-attention.
Well, and I think maybe this captures something key to what the bidirectional piece is doing, is that effectively, if you just input noise, if you input the first token and then input noise, allowed it to spit out the first token and the second token, you would hope, right? Took the second token from the top, added it to the first token, fed that in with the rest being noise, that would roughly be a left to right transformer model.
So,
right? Does that make sense?
Basically, what you think is like first left to right, and then right to left, and
well, the beauty of the bidirectional is that you literally could start in the middle, or you could be like, I want the first word and the last word, and I'm going to keep those. You could go like it's free to vary in any. It's like a
amazing for like poetry. Like you could have like a gist of something or like a rhyming scheme or like you just like fill in the rest of it.
Yes,
I think it's really cool.
And I think that the intuition that they're showing at the end with the fine tuning, when you basically say, okay, now what we're going to do is we're going to create some kind of secondary embedding space, like for the start and end of where we should look in a paragraph. You can couple that with the current state of the embedding to learn effectively like a joint distribution.
Can you explain more regarding the structure of the things? I'm not sure that I follow the structure. The part that again you mentioned about go back. More please. No. You go to the first.
Forward.
You move forward. So here. So the large one has 24 layers, and then in the last slide, actually it has a 24 transform unit.
Transformer blocks.
So the transform blocks are you are stacking up all of them.
Yes.
And then how this number of hiddens coming?
A hidden layer represents within each, it's a parameter within each transformer block. So the hidden represents the hidden size of the feed-forward network, I think.
So each transform block has the 1 or 24 hidden neurons, is that what you mean?
Yeah, I think, this definitely refers to the within each transformer block, and it's the same for each transformer block.
So it's like 24,000 total. Well, more than that.
So
Not
yes.
It's big.
So this is a parameter for within each transformer block. Does that answer your question?
Oh yeah, I'm trying to get into that 340 million parameters.
How they get this in the end, right?
Yeah, but I cannot see the connection. I'm not sure about the 16 head, how that 16 head going to play to let me to get at that number of parameters. I get close to that number of parameters.
Do you know what the heads? Do you understand what the heads is referring to?
Oh yeah. Okay. I remember this one.
I have a really left field sort of question. Someone during your presentation was talking about, I think misunderstanding the heads was talking about overfitting, right? in theory, if you could train on like everything that everyone has ever generated, would it be okay to overfit?
What does overfitting look like in this case?
Well, like memorization or what? Yeah, right. I guess that's kind of the question.
What
Natural languages.
I don't know,
But
like
it's
if your corpus is big enough, whatever that means, like to your
So you're
asymptote of
basically
huge.
saying if it's not a sample and it's a population, isn't it the population?
Yeah.
That is the
Yeah, can you fit to the population?
But
Like,
so
just-
then
just
then
to-
it's never overfitting, right? Because you have the
the
population.
entire population,
Yeah.
right?
And you got
Yeah,
it.
okay.
Is a natural language dynamic though? You can always make up sentences that have never existed. So you can never reach population.
But maybe the rules you're using are already ones that have existed, so it doesn't matter if.
But then you're back at overfitting.
Yeah, should overfitting
Because
by memorizing these sentences.
I think the intuition, instead of thinking
Right,
about it
okay.
in terms of the data, it's think about it in terms of the representation that you're trying to learn. So overfitting means that you've somehow tightly coupled to a single representation, which is the representation of your data.
Yeah.
Right? If you want to learn the rules that govern the representation, or you want your representation to be the rules that govern the thing instead of the artifact, then that's kind of, I think, what you're trying to wrestle with
Yeah.
overfitting. Does that make sense?
But I think that's a good point. So like nowadays we have big data, we have the entire internet. That's that's unfairly. So they're literally training these language models on the entire internet, and that's
Yeah.
unfairly large. And that's very close to the population. Like that's very
Right.
close.
So at what
So, yeah,
point?
that's-
Yeah, if you have enough, I don't know what the question is anymore, but if it's like, can you not? I don't know how to like define it anymore. It's like, is overfitting no longer
Well,
the
if you
concept
expect,
if your sample is your population?
if you expect that the data you're going to be bringing in an inference is going to still be within that
Yeah.
population, it's okay. But
Right.
if it's not, then
But then what? But if your sample is your population, then there is nothing that can.
well, I guess that's the argument. I would tend to agree that you can't capture all variations
Yeah.
of language.
You might run into problems if you're going cross-domain though, like if you're going from natural language to image, like image captioning or things like that.
Or
Potentially.
even within natural language, you have different subdomains, and what your population, what the parameters of your population indicate, wouldn't necessarily match the parameters in the say sample or another population for another task. As I don't know, predicting the next word in a technical, in a like medical domain.
So
the
that could be
parameters of that.
Sorry.
No.
No. So that could be a problem anyway. But the point then is that it needs to be generalizable enough that it will still work in a specific domain. I guess.
To expand on that point, though, I remember reading, it was more in a theoretical, philosophical almost sense about, and I think it touches on this big data idea, is that at some asymptote of amount of data,
Yeah.
some kind of weird behaviors, you're going to start having weird behavior effectively emerge.
Too much data.
But the weird, I think that maybe the interesting thing that maybe Ehsan is pointing to is that the question then becomes, how do you move within that space? Right? Even if I have all of the data, I want to be able to put some constraint on it that allows me to zoom in on some specific subset, even if if you literally had the true asymptote.
And the answer to that, we had a TDLS for that, contextualized language models. They do touch on that space.
Right.
And I'm kind of working on that in my thesis. I have a clarification question, if I may ask.
The time for that has passed.
You have to argue.
You have to argue.
Make
You
it
have
an
to say
argument.
it in an argument that you
I
want.
argue that clarification questions times has not passed. So
Motion passed.
Has the predicate.
just want to understand before I make the full comparison, because I wanted to do the cut period off earlier. I want to run a quick comparison between word to vec, but you need to understand a couple of few details and in regards to how this is trained. So you get the positive signal wherever you predicted correctly, and then you go back and for that mask representation, you say when it's positive, you stop training it. You basically say that's a good representation. Or I just want to see how you get the positive and the negative signals.
That's a good question. That's the mechanism of pre-training. My impression is that you have to both predict take both these, all masks, in a given input sentence. That's my understanding. That's my guess, actually.
You're wondering if there's any negative
What's
symbols
Yeah,
in that process?
because like if you predicted incorrectly, how do you
Penalize?
yeah, how do you penalize? How do your gradients actually move you towards a minimum?
Well, you apply the softmax and then you compare the result of that to the actual label. And then if
Cross entropy?
Yeah.
if there's a difference between, if you misclassify the mask token, then it should backpropagate the.
But it's the contrast. From what I saw, the contrast of samples, they actually just put a random embedding there instead.
For NCE, it's not really. So you randomly sample the negative. So in word2vec, what happens?
So
And that's a
just
very
quick
quick
clarification. I think the contrastive samples are for task 2, and task 1 is just this, like the softmax, and task 2
Yeah.
has the contrastive stuff.
Yeah, so
Not here.
so let me slip in sort of word2vec, and then because that's the context where my question arises. So in word2vec, there are two different ways to train them. Basically, the question is, you want to have your vectors that are efficient for language. You can't for each word. You have to for each word to predict each representation correctly. Only one representation is correct, and all the other vocabulary item representations are incorrect, right? And that's inefficient to compute. The way they do this NCE idea, where you take 5 negative samples and 1 correct, for example, and that's a parameter. So you have 1 positive signal, oh, this is the right one, and these are incorrect, and the binary classification, as opposed to your cross entropy, will tell you if I'm predicting correct or not, give you both signals, right?
Right, okay.
Yeah.
I think there might be something in the paper. There's, like this is just a simplified version of what it is. In the actual paper, you also replace the mask sometimes with a random word from the text.
There you go, okay.
So,
Or the correct. Let me get the paper out.
Or the correct one.
yeah.
Yeah. So I think.
Because this has to happen to get both information. So you just
because otherwise you're measuring the softmax against the entire distribution, which is insane, and would be so very because you would have to effectively you're kind of saying, what is my probability? How does my probability distribution compare to every possible other probability distribution over all possible tokens, which is continuous? It's a continuous space.
That's what categorical cross entropy is basically doing?
In the case when you're using an embedding, it's not categorical. But in a categorical sense, if your token set is small enough, I think. But because the embedding space is continuous.
Okay, yeah.
Yeah, so that's a really good point, I think, because like what we are doing predicting is actually predicting vectors, word embeddings. But then that's like exactly as you said, it's a continuous space. So then how accurate is accurate? So do we put a threshold of like the neighborhood of that is like?
That's what the sample thing is there, because if you have 4 bad examples and 1 good example, you can compare internally to that local subset of the total probability.
So then do we need to like humanly set like a hyperparameter of the threshold? Because like a continuous number is like so many digits, right?
But
it could be.
So are we talking about? Just want to make sure. Are we talking about word2vec or this?
This one.
This one? Okay.
But we're not actually sure of that.
Yeah, but I think he's trying to find the answer. The camera's capturing.
So
it.
let me just
Call out to Google and be like, hey, we've got a
Hey, how do you
question
do
for you,
this?
and send them a review.
So but very quickly to summarize, because we went overboard. So basically, you want to have, as Eric said, negative signal as well as positive signal.
So let me just read this to you.
Yeah.
What the actual, this is a simplified version, what the actual mask language model is.
Yeah.
So 50% of the words are replaced with a mask. 80%, well actually, every time that a word is to be masked, 80% of the time is actually replaced with the mask. 10% of the time, this will be replaced with a total random word, like apple. And the other 10% of the time, this word is unchanged, like a store. So you just put that in there.
So only two alternatives. Either it's the right one or it's a random word.
Yes.
Which is very similar to the idea of NC. Now, wouldn't your cross entropy change then?
I don't have cross entropy for this final task.
Yeah, because then it's. Oh no, that's actually a negative sample.
Yes.
You know that it's incorrect.
Yes.
And the embeddings have to be. So it goes to your cross entropy. It has to say if it's a binary classification, it has to say incorrect. But you said it's not. It's a softmax.
It is a softmax.
I'm just trying to figure out how that works.
Felt like they didn't go over this part super in depth in the paper.
Another question, so we are using the neighborhood word embeddings to predict that target embeddings. So then, where are those neighborhood embeddings come from?
So okay, we are not talking about a neighborhood at all.
Okay.
So that was okay. So that was word to vec. In word to vec, each word was a summation of. So there were two models again. There was a C-balance kickdown. One, each word was a summation of all the rest. The other, you get one representation. You try to predict all the rest, right? That was word to vec. Here, all you do, I assume, and correct me if I'm wrong, you initialize randomly. You have your transformer network, which is basically similar to CNN, and then you have attention. That's the most layman, that's the worst horrible summarization. I guess you can take a look at the previous talk to know how it works. And you have a softmax where it says you're predicting these maps correctly or not, and that's how you know that these embeddings are good ones or not. So that's where
So for example, when you're trying to predict mask 1, and then you need to input the man when to the. So then, how do you represent the man when to the? Just like the text itself, or a vector?
Oh, you represent each one of these as a vector. So each token is a pre-embedded vector.
Right, so it's a representation of each of these tokenized
Right.
words. And then where did you get these vector from? Like from some pre-trained elsewhere?
It's from a pre-trained model called WordPiece.
WordPiece.
Yeah, so it uses a different tokenizer, slightly non-standard tokenizer, that will split words into their subunits.
Right.
So that was the example I gave earlier was the word playing is divided into two tokens, play and ing.
Yeah, it's right there. So those are the tokens. But I think her question is those tokens, think, ing, yes, those are the tokens. How do you represent them?
Well, the word piece embedding has an embedding for each token. Yes.
Yeah. So that's how was that?
How was that
created? How was that created?
That came from a paper from 2 years ago, also from Google. They just took their pre-trained model. I didn't dive into that paper.
Yeah. Okay. And do they compare? Sorry, very quickly. Do they compare with randomly initialized though?
I have a comparative question. How does this compare with ULM, which I know they're not exactly similar, but it doesn't make sense to pre-train a model. And so the idea is when you pre-train, let's say, on Wikipedia and book corpus, now you're learning the Englishness of the language, but you suddenly want to do classification on, let's say, domain text, and you're not learning the domainness of the text just by using the penultimate layer. So why? I mean, it's more of a discussion. I don't know, what do you guys think about? Shouldn't we maybe fine-tune the previous layers too?
They do fine-tune. That's the last stage.
But they fine-tune only the sequential layer on top of the pre-trained,
as opposed to the whole.
Yeah.
Yeah, I think they actually do fine-tune on the whole.
Okay.
But that's only for them.
There's some uncertainty.
So since we have 5 minutes, do you want to quickly go through the discussion points?
Okay, so let's see. I have one discussion point, which one you already saw, which is this crazy question: can we combine this with a stacked pre-trained transformer decoder with machine translation? And my other question, which is an open-ended question, will we ever need to train models from scratch in the future? If things like this, pre-trained models, we can just use this and just fine-tune it easily. We never have to do anything from scratch again.
I think that's
These were my discussion points, yes?
So for the first one, allow me to ask, is anybody familiar with beam search in this context?
Beam
In
search, this context.
Yeah, I mean,
So we have a long discussion about beam search in one of the videos from previous sessions.
oh,
We were like talking about it for 10, 15 minutes.
Well, I wanted to
We're now
finish
in
his
it.
discussion.
Right, so let's finish this and then we get to that.
okay.
Did you have something else? Sorry.
So these were my two, and then I have some from Gordon and Florian too. You want to see those?
Yeah.
So Gordon's discussion point was about the.
What's an ablation study? Ablation is kind of like amputation, but for like
Yeah.
hearts and icebergs.
It's where they remove part of their procedure, their model, some aspect of their initial study,
Okay.
and then see how well it performs without that.
Compared to the next leading one, OpenAI GPT.
They remove some
So
aspects.
for example, they remove the mass language model training procedure in one of them. They also remove the bidirectionality. So they were just using a left to right architecture. And then they evaluate how well does it do.
Compared to their full model and compared to other
Yes.
people's models?
Yeah, the idea
Oh,
being,
interesting.
where is the novel boost coming from
Right.
in this paper? What is the aspect that we can't remove without the results going down?
Right.
And my biggest, really, there's a lot of text here, so don't really have to read it. But really what my biggest concern was, in these studies, they're generally comparing to OpenAI GPT. That's
right.
one very similar historical paper. But what they never do is they never train both models on the same data.
Yeah.
So the OpenAI GPT model is trained on the book corpus data,
Right.
which they're also training on. But the book corpus data was something like 800 million tokens.
That's right.
But they also train on Wikipedia, which is
3 billion.
Yeah, about 3 billion tokens, so much larger. And they never did an ablation study where they removed that and trained on the same data, or added that training data into the OpenAI data. And it seems like a very obvious potential. I mean, I don't want to say that the result would be null without that, but it seems like it's very possible that if you were to provide the same training data to OpenAI GPT, it could perform as well. Maybe.
So like, is the model better, or is it just really a well-read model?
Right.
Training.
Yes, on that note, Royal mentioned that as well, the ULM fit paper, they trained on Wikipedia too, they didn't compare to that even.
Yeah, I find it very disconcerting that at least at one place, just at one place, they mentioned ULM fit, but like completely forgo this thing, given the fact that it was published this year.
I think maybe the reason they didn't do the comparison is because that's actually like an RNN model, whereas this is the transformer, so it's not apples to apples.
Well, they do compare it somewhat to Elmo, which is a RNN model, but they mainly do it to OpenAI GPT, which they consider their nemesis.
So GPT is also an RNN model, right?
It's a left to right transformer model.
Yeah. So which means the second half is technically an RNN. Or sorry, I mean it can be used to. It's kind of a recursive generator.
Like it can generate sequences, like
Yeah.
generation.
So
Yes.
that makes it RNN generator.
It makes it a sequence model.
So the recurrent part in the generator does not make it an RNN.
There is no recurrent part in the transformer.
Okay, sorry, my bad.
So what is the second one?
Second one, it's a lot of text. Hard to remember.
I don't remember this one as well.
Okay, let's move on.
It's like,
It's
are
not
they
important
really-
enough, otherwise
is
it
it
would
as
have
much
been.
of an improvement as they think it will?
Yeah,
It
okay.
really is.
Okay.
Yes. So Gordon has some good doubts about this paper, especially this one, that they should have maybe removed the Wikipedia corpus. Then for Florian, who's not here, that he has some other discussion points. So in this one, he refers to the actual mass language model. They randomly replace 50% of the tokens, and then 10% of the 50% is replaced with a random word corpus. what is the importance of this step, and do his leaving out results in both forms decrease put together? I think, Asan, you were answering this question earlier on.
I think so.
Well, I think, so I look back at the paper and it seems like they are doing what you were saying, Ehsan, right? So they're adding, those different conditions, they're adding different things to the comparison component of the softmax, right? So I think what it's actually doing is it's trying to push away, like I thought 10% was that it replaces it 10% of the time with a real word, but
yeah, 10% is real word, 10% random word, 80% math.
Yeah, so I think it's just trying to push it away from the actual real word some percentage of the time.
Yeah, so the question is, you want, with only the positive signals, you get it, what this representation should be close to,
Right.
but you're not getting what it shouldn't be close to.
Yeah.
That's why you need the negative samples, right? And they're doing a decent job with like having like categories and then picking from those categories. The synonym idea is interesting. That's technically a negative sample. That's a hard negative sample. And I think they did a good job there. And in that regard, then, they're very similar to Word2Vec. It's just that they're doing a better job in picking their
negative sample.
The negatives.
Right.
Isan, to your point about the noise contrastive estimation, if I recall correctly, in the original paper, they mentioned the reason they were doing it was because the vocabulary size was too big in the softmax, and that caused issues with even getting
So
the
that's
right
part of it.
outcomes.
That's the sampling part, right?
Yeah.
In general, you want to have, yes. So that's why you only randomly pick a few.
Yeah. But like other papers, like the ULM Fit one, they also just did a softmax over the
whole
vocabulary, no
category.
noise contrastive part there, and their model works, I guess, fine.
Is it better?
Well, they didn't compare it to this, but
Yeah,
6 months ago.
Transformer also?
Yeah, I think it's just
I don't know about
Quick.
transformers.
I think the other paper that Gordon and I were reading is Quick Thoughts, where they overcome this problem by encoding a sentence as such, and then I think they do RTE, recognition, textual entitlement, basically, I think, and then they have negative sentences and one positive sentence in the candidate sentences, and then they encode it and have a classifier on top of this. So that basically avoids softmaxing over the entire vocabulary.
Yeah, so the basic, a very strong point of NCE was back then to, well, the main point is you want to have your noise in order to contrast, in order to better estimate, so that's why noise contrastive estimation. But the reason they sampled is because they couldn't go, computationally it was not infeasible to go through the entire vocabulary. If nowadays we can do that, that's amazing.
Yeah, 64 TPUs, remember.
Yeah.
Did you see the estimates for training if you were to do it on your own computer? It was like
4 years.
200 something days or something.
Yeah.
Really?
Yeah, it was like 4 days on TPU. And
This is why you should
When
rent
you look
TPUs.
at the natural language problem, you think that these BERT cannot solve or has a poor performance on it?
Other NLP tasks, actually some of natural language understanding. I don't know what other NLP tasks are. Probably a lot, but I can't think of any.
Sentiment analysis.
Because apparently,
Translation and all.
Yes. Translation, I don't know about that. So you have to, it'll be difficult because you have to actually generate the output, right?
because I wonder, do you guys also feel that those problems that it showed in the paper is not a really hard problem? I know that you get a good result to beat the state of the art by one person, I agree with that. But we have a much more harder problem if you have the natural language understanding. We have tons of them.
So question answering isn't easy. It's one of the hardest.
True.
Right?
True.
Although their frame was a little bit, it was just from the paragraph, right? It could be 3, 4, then it would be
Insane.
Sorry?
Insanely hard.
Yes, and that's called conversational agents. That's super hard. Yes,
Yeah.
that's. But so the first point I wanted to answer, I forgot what your first question was, but I think.
I was wondering that what type of the problem think that the BERT is not capable of handling or have the full performances?
I think it's fair to test and compare. I think when you want to compare and do these evaluation studies, you have a lot of restrictions. What people have done previously, and it's usually you usually do pick the tasks that are very clear and the scientific community has a good understanding of. So like conversational agent is super hard. I'm not sure if you have a global metric for to assess.
But isn't part of the question just like where would it fail to generalize? Right?
Yeah.
So where if you could guess where it would fail to generalize, I think that's a very hard question. Like where, because it's sort of like asking where would you intrinsically not be able to use word to vec, for example.
Or in another word, now you want to use the right, and you have a set of problems. Which one you are going to use this one there, and then here this one going to solve it?
I think they literally mean it for everything with language.
Yeah, because like representation. So and that sort of answers the previous. Yeah, that answers the previous question. I think somebody asked. So basically, you can use these embeddings for machine. Oh, okay, that was the question. So if it can be used for machine translation, for example. So the transformer network with machine translation started off, I think, randomly initialized vectors for the words. You can use these as
in the encoder.
Yeah, in the encoder.
For translation.
Yeah. Well, you can start off your because in translation you have your embedding dictionary. That is the next step after one harmonic recording. So you still can you start off with much better representation if you use these as opposed to. And I guess that the same goes for speech recognition and every other task.
Yeah. Okay. Yeah.
Okay.
Thank you, everybody.
Hard task.